So now that we have it, let's use it. Let's go to the Chapter 9 slides. I said they were working. Here we go. Yeah.
Can we use PDF when you put it here? It's difficult.
The HTML.
It's not easy to download.
It's not easy to print. Yeah, it's not printable. So these slides are, other than those 2 PowerPoint that we've hit so far, all of these slides are written in R. And so the 2 PowerPoint chapters we never got around to switching over, but this is in R. In fact, you can write, let me show you how, now that you guys have had some experience in R. So this is all coming from GitHub. So where's my GitHub? So here's GitHub. Anyone heard of GitHub? Yeah? So GitHub is a place where you can house files. You may have an account, kind of like Box, but it's mostly for, it's free. It's mostly open source programming things, not just in R. So this is mine, but Tyson and I have formed this organization. This is where all the public files, all the slides, and the assignments and stuff are living right now. I just wanted to show you an R file that makes a slideshow. So here is, see, we're doing Chapter 9. So here's the Chapter 9. Okay, let's see. It's showing it right now. I could open it in R. In fact, let me do that because then it'll look the way you're used to seeing it. I was working on this today. So the slides are going to be in not the public, but the private. No, they are in the public. So, okay, check it out. This is an R file that makes a slideshow. Let's see, how familiar is this? At the very top, what does it look like? We have a title. You can give it a subtitle. And then output, this is a certain kind of slides, and it's this guy, that's his last name. I don't know how to say it. Made these slides, like the ability to do this in R. So we set up the chunk options. Does this look familiar? Now the way you do it if you want to center text, you just say class centered middle. If you want like the text in the center in the middle of the slide. And double pound makes it like a bigger section heading. And to do a new slide, you do 3 dashes. That does a new slide. How easy is that? So every time you want a new slide, you do 3 dashes. And we've done a lot of fancy stuff here. So we wanted like text on the left and text on the right, 2 columns. So you do pull left and pull right. But I mean, it's just like you just write your R code. But the nice thing is, what if you want to put a figure in there or show a data frame? You can put R chunks right inside your document. And then when you knit it, instead of making a PDF, it makes the slides. And it makes them in HTML because they're easier to put them on a website. It does not make them good for printing, right? So the HTML slides are not good for printing. Also, this is a dark navy background is what we chose for the title slide, and that's not fun to print because it's going to suck a lot of ink. So yeah, so the links on that website are to these HTML, and I realize they're not great for printing. You can convert them to PDF, but the problem is we've been updating these slides, and every time you update them, then you have to go and change it back to PDF too. And so that's something that I haven't kept up on. So if you want to, let's see, can we do it? I don't know how. Actually, Tyson was the one that did it.
If you just print it and make it a save as PDF.
Yeah, print, save as PDF.
Yeah. It's easier. It's easy enough to do. Enough. It's not great. So we can print. So print to save as PDF. Yeah. Can you do, pages per sheet. So you can do like 2 per page. So they're not like ginormous. Yeah. Is that okay? I'm sorry. if it's too big of a deal, we
I
can.
have the R file.
Uh-huh.
So we can learn that.
You can look at the R file. If you want to learn any of this, I'd be happy to show you. I think it's like super chill, super fun, but I'm kind of like a huge nerd, so. So we were doing correlation before, right? So we saw the Nicolas Cage films and Drowning Deaths, and we said they're associated, but that does not mean those two things are causal. It might be an association, but it might be kind of a spurious finding. Spurious finding means it's like trivial, it's not meaningful. So we said it's always important to visualize your data. Why is it important to visualize your data? Because you might have very little variability, you might have nonlinear trend, you might have a influential point, an outlier. Yeah, so there's an outlier. Okay, so I think that's the last slide. We didn't see this slide yet, did we? Okay, so like when we did the mean, when we're doing symbols, if it's the mean in the whole population, we used what symbol? Mu, the Greek mu. And if we're doing standard deviation for the whole population, it's sigma, the Greek symbol. So we use the Greek symbols for population parameters. So for correlation, this is rho, R-H-O, rho, like row, row, row your boat. No, but rho. And then, so when we use the lowercase r, that means correlation in a sample. So usually that's what if we have a number, it's almost always coming from a sample. But we really wish we could know about the correlation in the whole population. So that's our best guess. Our sample statistic is our point estimate for our population parameter. So the R, whatever number we get for R, tells us direction and strength. Positive number means it's high on one is partnered with high on the other. Low on one's partnered with low on the other. Negative means high on one goes with low on the other, and vice versa. And the biggest the R can be is perfect relationship would be plus or minus exactly 1. But that influential points can have a big influence. How do you like that equation? No. Okay, let's break it down a little bit. And you're not ever going to be asked to do this by hand. Never. In this class or otherwise. You don't even worry about that. But let's see what's going on here. We're taking all the x values, and what are we doing with all those x values? Because it says I, indexing 1, 2, 3, 4, 5. We are subtracting the mean and dividing by the spread, the standard deviation. What's that called when we subtract the average, divide by the spread? That's a z-score. So we standardize or do the z-score of all the x's. What are they doing over here? Standardizing or doing the z-scores for all the y's, and then they are multiplying them together. That's why this is called Pearson's product moment correlation, because you do the product, so you take your x's and your y's, and you make them both z-scores, and you multiply them together. And then what does this say? Add them all up and divide by degrees of freedom. One less than the sample size. So basically, we were averaging, adding them up. Usually when we average, we add up and divide by however many we had. It's one less because it makes it unbiased. It's the easiest way to tell you the reason, is because we're going to use degrees of freedom, because this is based on sample information, not the whole population. If we had the whole population, we'd divide by n.
Is that n just the
Number of pairs.
okay, pairs?
Yeah, so n here is the number of pairs because it's the number of people. X and Y pair per person. So yes, that's a good point. N is the number of pairs of X and Y. So if we had IQ and driving ability, I don't know, we'd have both of those things measured on one person. So we'd have n would be the number of people we had. So we'd have n would be how many x's we had and how many y's. You have to have both to be able to do correlation. People that only have one but not the other score cannot be used in correlation. You have to have complete pairs. So this is how you do it in R. You ready for some intense code? Oh, where did it go? thought it was going to show us our code. Oh. Oh. I see what this slide is. Okay. Here's the original data. Here is when we change x and y to z-scores. What do you notice about the picture? Nothing changed. When you do the z-score, subtract the average, divide by the spread, it changes the units. It does not change the shape at all. So the shape, the units down here, instead of being from, let's see, it goes 10 to 30 are the numbers. Now it goes from -3 to +3. So when we make the z-score, it changes the unit. And that's why it's always between -1 and +1, because we've changed them to z-scores and we're multiplying the x's z-score and y's z-score, multiplying them, and then adding them up and dividing. So it always makes R, the correlation coefficient, always between +1 and -1, which means that there's no units in it, which is nice. Okay, so here's the code. It's really hard. Start with the name of your data set, your data frame, and pipe it into the next step. We always do that, right? And it's core.test. This is in base R, core.test. And then inside the parentheses, we have to put some things. The first thing we put is the formula. Now, we use this tilde wave. We've seen this before to write the formula. Now, x and y are the variable names. This is just this is example code. We'd put whatever is the name of the x variable and the name of the y variable are here, and we put a plus in between them. Now, it's important to note, where are the two variable names placed compared to where the tilde is located? X and y, those variable names are on the same side of the tilde. This is important because when we do regression, we're going to have one variable name before the tilde and one after the tilde. But for correlation, the variable names are on the same side of the tilde. They both come after the tilde. Is there a problem? The tilde, oh yeah, it's above that escape key, over by your escape key. Yeah. I call it tilde. That's the math name for that symbol, is tilde, yeah. So now, the thing with correlation, when you're calculating correlation, remember that formula. We did the x made a z-score, y made the z-score, and multiply. When you multiply, does order matter? Not at all. When you do correlation, the correlation of x with y is the same thing as y with x. So when you put the names of the two variables in here, order does not matter. The correlation order does not matter. Correlation of these two variables is the same thing as the correlation between these two variables. I make that distinction because when we do regression, it does matter, and that's the next chapter. So we want to make that really clear. So for correlation, we're going to put both variable names on the same side of the tilde sign with a plus between them, order not mattering, but which one comes first. Data equals dot, and we have to say method equals Pearson, although I think that might be the default. And this is what it will give you. This is the output. It's very, very nice. It tells you this is Pearson's product moment correlation. It tells you the whole name. Usually when we say just the word correlation, usually this is what we're referring to. So most people just say the correlation was strong, R equals. Now for correlation, R, like all software, is going to put a 0 in front of that decimal, but do we need it? No. Because is correlation ever going to be 1 point something? Never. It would be exactly 1 in a perfect world, but that's never real life. So correlation here is 0.05. Now it gives us a t-test to see if that's statistically significant. Let me write on here. So how would we write this in a sentence? This is new. They changed all that. They changed it. I don't like that. It used to be I click there. Oh, where'd it go? Okay, so here, x and y, we're going to say are some important variables. Are we not? It's not even writing. Okay, we're going to go on the board here. Lovely. So let's see. Let me see if we can get this to pick it up so that it's in the video. Can you see the whiteboard? Okay, so x and y, we're going to say that they're meaningful variables. Here it's just an example, so they're not. So what's the correlation in this case? R equals, what was it? 0.05. Now, how many decimal numbers do we put after a decimal point? We're going to always, in this class, do 2, except for 3. During calculations, we're going to keep 4, and p-values, we're going to keep 3. So the correlation is 0.05. What do you think about that strength and direction? Very low strength, positive direction. So there is a very slight positive correlation in this data. But then, what's the t? How would we write the t? 98. And I'll tell you, that's 2 less than the sample size. In correlation, the degrees of freedom are 2 less than the sample size. And that's equaling, do we put the 0 in front of this decimal place? Yes. We have to, because t-values can be 1 point something, or 2 point something, or 37 point something. And then 5.3. And the p-value, do we need a 0 in front of this decimal place? Nope. And how many numbers are we going to put after this decimal? 3. 5, 9, 4. So if I was writing a sentence, I would say there was only a very slightly positive correlation in the sample, which was not evidence that there is a correlation in the population. So there's not statistical significant evidence of an association. Not. Question? Okay. So here is another. So this code will give this output, and that's how you read it. Now, it also gives us a confidence interval around that correlation. What do we notice about the confidence interval? If we were going to write that, we'd say comma 95 CI, or usually, let's see, APA says 95% CI square bracket negative 0.14 comma 0.25. What do you notice about the confidence interval? The littlest number is negative. The biggest number is positive. And zero's in there. So it could be negative, it could be 0, it could be positive. So, not any evidence that there's one way or the other, because it includes negative, 0, and positive in the interval. So no evidence of an association in this case. Oh, the other one. The other option for code. If you only have 2 variables, this is not so great, but this is nice if you have more than 2 variables. So often we want to know, are any of these 5 variables associated with each other? And to do that, we usually do a correlation matrix showing all possible pairings. Tyson added a correlation table into furniture. His packaged furniture has table C, this function or command. Inside the parentheses, you list out the variable names separated by commas, and it will make a nice matrix. And so you will always have ones on the diagonal, and the top half will be blank, because it's just a mirror image of the bottom half. That's how we do correlation matrix. So notice, what do we get right here? It says 1 is X variable, 2 is the Y variable. So this number right here is between 1 and 2. So between X and Y, the correlation is 0.05, and it's not significant. So this is, if you have a lot of variables, this is a nice way to display all the correlations. But this is what you'll need to do the homework. Core.test, that'll give you everything you need. Okay. We already talked about what's going to be the correlation if I calculate R for this set of data, the second one right here. It's going to be close to 0, because what's the line of best fit? Well, here it's down, negative, and here it's positive. So if it tries to fit one line to this whole data set, it's going to be fairly flat. Not a good idea. That's why we want to plot our data, because correlation does not do that. Okay, so we did the app before. Okay, assumptions. There are assumptions with every statistical model. Correlation assumes that we have a random sample so that our data in our sample represents our population. Can we test that? Can we test if our data is random? No. Can we fix it if it's not random? No. How do you make sure it's random? No. You plan as well as you can that at least it's representative and random as possible. Number 2 assumption. Our assumption is that a linear pattern exists. Can you check if the pattern is linear? Yes. How do you check if the pattern is linear? Plot it. What type of plot is that called? Scatter plot. And what geom do we use in ggplot? Geom underscore, it's not scatter. Scatter's nowhere in the code. Point, geom point. Yeah. Okay. Now this third one, huh?
And then homework though, you had to use it differently.
Geom count?
Yeah.
Geom point or geom count? Yeah. Okay. I'll show you the difference. The third assumption is that we have a bivariate. What does bivariate mean, do you think? Bi, 2 variables, that both of our variables together have a it ends up being a 3-dimensional normal distribution that looks like this. It's a crazy figure. It's this nice. So we've looked at bell curves in 1 dimension, 2D bell curves. It's like a bell curve in 3D. So for this to be true, each variable should be normally distributed by itself. And then if you plot them together, you should get this. The way we really do it in real life is we make a scatter plot and make sure it's not curved. If it's linear, if the scatter plot is linear and each variable is normally distributed, then this is true. Okay. So rho has a distribution. We can do confidence intervals. So when we are doing correlation, our null hypothesis for this t-test, we ran it in the syntax before we talked about what it is the null hypothesis is that their rho is 0, which means the association, nothing going on. Remember, the null hypothesis is always nothing going on. The null hypothesis is no association. So rho equals 0. So the alternative is that it's not 0. That's the two-tailed test. So the way that you test that is R gets converted to a t statistic by this calculation. Now, R did it for you. It took the correlation and the sample size, and it calculates it, and it does it for you. Isn't that nice? So here, it takes R, and it multiplies by the square root of n minus 2 over the square root of 1 minus r squared. And that calculates a t, and the degrees of freedom are sample size minus 2. And there is a table for that t distribution. We've used it before, right? Yeah. So that's how you know if it is or not. So here is a real variable names, not just x and y. So researcher has data on 7 people. It's right there. Has 2 variables. One's called their mood, their current mood state. I don't know how they measure that, but they have their mood as a number. And they have their verbal recall, how much they recalled on some test. So person number 1 had mood score of 45 and recall of 48. And you can see all the pairing. So what's the sample size? 7. So how many degrees of freedom for the correlation? 5. So here is, took the name of the data set, did core.test, nothing in front of the tilde wave, the 2 variable names added together after, data equals dot. You can say method equals Pearson, but you don't have to because that's the default. And here's the output. Let's see, what does it look like? The correlation, direction and strength. Positive, moderately strong, positive correlation. Not significant. Is that surprising that the correlation would be 0.65 and not significant?
The degree of freedom is pretty low.
Yeah. How big is this sample? Small. It's a really small sample. If we had 70 in our sample, that probably would be significant. So it's important to remember that the power of a test is related to how big your sample size is. Remember we did the G power before? Your power and sample size were directly tied together. So if you have a bigger sample, the p-value might change. Okay. So here is, getting chopped off at the bottom of the screen, the formula that we use to find out how many people we should have in a sample if we want to do a correlation test. We got D at the bottom and a delta, uppercase delta up here, squared plus 1. D is a value, the delta value, from a table in the back of your book that I'd never seen before I taught out of this book. And so you know how often I use this formula in real life? Never. What do I do if I want to know what sample size I should get? I use G-power. You can go to G-power to t-test, and that for the family test, choose T, like we were doing before. And the type of analysis, instead of choosing difference in means, you choose correlation. And then you can get sample size calculations. But there is a formula that it's using. So let's see. Here's an example. Based on a pilot study, remember, to do a power analysis, you always have to have an estimate of the effect size. And that is based on prior research or pilot data. So if you're going to ask someone for money, they're going to want you to do a sample size calculation, a power analysis, to show them that you're getting a big enough sample size that their money is well spent, but not so big that you're wasting their money. So if I wanted to do a study, I want to check the pilot, I went out and got a little bit of data, and in that sample, I saw the correlation was 0.6, and I want to know how many people should I plan to recruit for a full-blown study if I want to have 80% for a 0.05 two-tailed test. Now, we could use that formula, or let's do what we do in real life. Let's do G-power, shall we? So what are the important numbers we need to remember here? 0.05 is the alpha, 80% power, correlation, that's our effect size, is 0.6 based on pilot data, and two tails. So let's go to our G-power. So we said we're going to do a t-test, and we're going to do it for correlation. Now, when you go to correlation, there's different, it says point by serial correlation. Yeah. There. It's under here as a z-test. We're going to choose correlation between two independent, no, not between two. Tetrachloric, let's do that first one. Let's do the T. Let's do the point by serial model. So a priori, compute the sample size. Number of tails, it defaults to 1 for no apparent reason. 2, effect size. Huh? What do we want for the effect size? Was it 0.8? 80% power, but the correlation based on the sample data, or the, yeah. So if you can squint your eyes and see from back there, it says effect size, and then it says, what's the symbol there? Row with absolute value bar. So if it's negative, you throw the negative away. So that's where we put our 0.6. And did you see when I hovered there? What does it say? Oh, can I get it to do it again? Probably not. There we go. 0.6, is that small, medium, or large? That's pretty large. So 0.6, alpha, 0.05, 80% power. Calculate, how big should my sample size be? 17. If I want to have 80% power to detect a large correlation, I need 17 people. What if I want to detect a correlation of 0.2 without doing don't click on anything? What's going to happen to the sample size requirement if I want to be able to detect 0.2? Is it going to go up or is it going to go down? We want to be able to detect smaller correlations, then we're going to need more sample. Let's see, let's try it, let's see. How much more, how high do you think it's going to go? Any gut? Significantly? 191. So when you had a sample size, or when I put up that sample with only 7 in it, what do you think about sample size 7? Only going to be able to have power for really big effect sizes.
Wait, wasn't that the Pearson correlation, though?
Uh-huh.
So shouldn't it be harder to get a bigger Pearson correlation? So you'd need more people?
It's to be sensitive enough to detect small differences, not to cause big differences, but to be able to detect big differences. So if wearing a seatbelt made a small difference, I would need a lot of people in my sample. If two things are only weakly correlated, I need a big sample to be able to establish it. So we're not causing a bigger effect, it's being able to be sensitive enough to declare a small difference as statistically significant via a p-value. Yeah. And it's always counterintuitive, as you would first think. Okay, so correlate or R. Can R be anything? No. R has limits to it, the correlation. Because what's the biggest that correlation can be? 1. What's the smallest it can be? -1 or 0 if you're looking at absolute value. So there are limits on it. And because of that, if your correlation is really close to being plus or minus 1 or really close to 0, it's not normally distributed because of that. So it can be, we already saw that it can be inflated. So that makes it be able to be inflated or deflated if you have a small sample size. So with correlation, you really do need a bigger sample size. How big? Well, it depends on how big of an effect you want to have, be able to detect. We already saw on the app it can be influenced by outliers, and we also, because of that range, what you're doing with correlation. If you think of data points, remember on a scatter plot, points, correlation is like where would be the best line? Are the points forming a line? If we have a restricted range, it's very hard to be able to detect that difference. So if I want to know correlation between IQ and reading ability, I don't just want a big sample. I want my sample to be very diverse across a wide range of IQ and reading levels. What if everyone in my sample has IQ between 90 and 110, or versus IQ between 99 and 101? So it's not just having a big sample, we want them to be heterogeneous or spread out amongst each other on the variables we're measuring. So if I'm doing a study on reading, I want to have people across the spectrum of reading ability. Or if I'm want to know if depression is associated with annual income. I want not just to have a big sample, but I want them to have a very big spread of different depression levels and different income levels to be able to be fully powered. Okay. There's a big, scary not equal sign. Just because two things are associated does not mean that the relationship is causal, especially in an observational study. Observational. Could be, but not necessarily. So we're going to look for strength, direction, and statistical test. Okay, so I wrote the R value and the T value separately, but the T value is just a recalculation of R value based on the sample size. So usually in APA, we write it like this. We do R, and after the R, we put the degrees of freedom, and we don't even report the T score, but we do the p-value. And then the confidence interval is a way of showing the effect size, because it's the range. So that's how we do it for APA. So here's some examples. Up here we have a little tidbit out of a fake write-up. So it says, for the 9 students, the scores on the first quiz, mean equals 7.00, standard deviation equals 1.23, and the first exam, mean equals standard deviation, were strongly and significantly correlated, R with degrees of freedom and p-value. So I always test myself, like I try to write the sentence without the numbers in it first. So if we ignore all the numbers in there, for the 9 students, the scores of the first quiz and the first exam were strongly and significantly correlated. Then you just jam in your numbers where they go. What do you notice about means and standard deviations? They are inside parentheses. What do you notice about R and the p-value? Not in parentheses, just separated with commas and a period at the very end. Okay, what things, let's look at decimals. 2 numbers after the decimal, 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 no 0 in front of the decimal point. 3 numbers after the decimal, no 0 in front of the decimal. The exceptions are degrees of freedom. If they're whole numbers, you don't put a decimal point. Now, why didn't they just write 7? Did they really need the 0.00 there? The rule is 2 decimals, but why couldn't we why is it important to show 0.00? Anyone have any ideas? Because of rounding, we want to show the accuracy that it could have been a decimal number because we are averaging here. So that's important. And 9, that's our sample size. What do you notice about 9? Is written out. Why is it written out? What's that rule? Less than 10. I think 10 we write T-E-N, but 11 we can write 1-1. Okay. Now here is out of another journal article. I think this is a real journal article here that I Skyped it. I chopped it out. Here's a table. This is it says correlation coefficient values. Now this one says Spearman's row. Spearman's is a different kind of correlation, and it's useful when you have other kinds of correlations. But ignoring that, notice we have all the variable names written out here, and then we have them written out here. If we had a diagonal, they would be perfect 1, so they don't even show that. And then the upper triangle is always blank because it's just going to be a mirror image of the bottom. So let's see, this first number here, 0.82. Now, what did they do wrong here according to APA or what our rules? They don't need that 0 in front of that decimal point. But again, some journals follow their own rules even though they say they're APA, so whatever. Anyway, so we've got 0.28 with 2 stars. And then down here, they tell you star, asterisk, level of significance obtained after Bonferroni adjustments. They didn't tell us it was 2 stars versus 1 star, but usually 2 stars means it's p-value less than 0.01. So they have not put the p-values in here, but they put stars instead. So what is this 0.82? It's the correlation between what and what? Age and age of onset. So this is, I don't know what this is, but age is different than age of onset, but they're highly correlated. And let's see, what other correlation is significant here? Yeah, positive symptoms and disorganization or positive symptoms and age, highly correlated. So the older they are, the more positive symptoms they have. Pretty strong correlation. Yeah, it's really hard to read. Now look at this one right here. If you can't see it, this is about negative 0.79, and it's got an asterisk. So that's strong and negative. So this says disorganization symptoms and positive symptoms. So those two are negatively correlated. So it means if you're high on positive symptoms, then you're low on this disorganization symptoms. Now it is nice. Notice they have abbreviations here. What did they put underneath here? Can you see that? It tells you what those abbreviations are for. And that's part of making tables. If you use any abbreviations in the table, you have to say what they are underneath, even though you said it in the paper, because the table should be able to stand on its own. Okay, so correlation matrices. Okay, let's see some more examples. This is the cancer data set. We've seen it before. Reading it into R. Okay, so let's see. The name of the data set is Cancer Clean. We're going to test the correlation between two variables. Do we remember what these variables were? This first one is the total oral condition at intake, and this is the oral condition at week 2. So it's baseline and week 2 values. Data equals dot, alternative equals two-sided. You can do a one-sided, but the default's to do two-sided, the default's to do Pearson's. How do we interpret this output? Because this is the kind of thing that's going to be on the test. You might be given this and say, what does this mean? Write it up APA style. Oh. What number should we look at first? The correlation. What's the correlation? 0.31. It's what's direction and strength? Positive. Small, slightly moderate, small. There is some positive correlation. Okay. What else do we need to look at there? P-value. Not significant. So what would be like the headline in the newspaper article?
Even though it's a small positive correlation between, I can't remember what they were.
In the sample,
Yeah.
the baseline and 2-week conditions are slightly positively correlated, but this is not a significant association. So we see a slight, but this is no evidence that it exists in the whole population. So that tells us, if we know what their baseline value is, does that help us know their 2-week value? Not really. No, not really. Okay. So here are some different options you can do. Now, all 3 of these have Pearson as the method, because that's the only method we're going to learn. But the alternative is different. So this one says alternative equals two-sided. This is the default. But you can also say alternative equals less or alternative equals greater if you want to see if it's less than 0 or greater than 0. Because what's the null hypothesis? It's equal to 0. So this is seeing if it's not equal to 0. This is just testing if the correlation is less than 0, so negative. The correlation is greater than 0, so that would be a positive correlation. I think the homework might ask you to do one like that. Okay, so here's the correlation table using more than 2 variables. So again, in both of those, we start with the name of the data set, furniture table C. The C stands for correlation, and then you list all your variable names with commas. So this is looking at the oral condition at baseline 2 weeks, 4 weeks, 6 weeks. What do you notice down here? Ooh, does that look great? What do you think about that? NA. What does NA mean in R? Missing data, missing data. Yeah, so by default it does, it says I can't do this because some people are missing the week 6 value. By default it does what's called pairwise deletion. No, it's doing listwise deletion in table C. So what do you do if you want it to ignore when it's missing data? Ignore cases with partial data? na.rm equals true. True. Yes, remove the missing values. And then it will complete the table for you. Did any of the numbers change, though? Besides replacing the NAs with values, it did. Because up here, this correlation is for all people. This one is just for those that have complete data. So sometimes we want this, sometimes we want that. I just want to show you how you can do it. So if you get NAs in your correlation matrix, that tells you have missing data. And you might want to say na.rm equals true, but then no, it gives you these values, but it changes the other values because it is only on the subsample that has complete data. Okay, so there's the scatter plot. So to do a scatter plot, it's geom point. if you want to put on the regression line, geom smooth, method equals LM in quotes. The LM stands for linear model. It'll draw the regression line. And by default, it will do this gray band around it. That's the 95% confidence band for the mean. Now, let's see, is the next one? Okay, good. Yeah, this is what I told you. So this is geom point. Geom point's really good for doing a scatter plot. But sometimes this can be problematic because what happens if 2 points land on top of each other? It'll look like one. So that's what geom count does. Now watch, I'm going to change it over. So there's geom point. There's geom count. So what happens if 2 points land on top of each other? It expands out. It like 2 drops of water. If you have a drop of water and you drop another one, it like expands out. So the size of the point shows you the count of points that would land on that spot. So this is really good if you have overlapping points. And so I use this a ton because that happens frequently. If your, scale, could only be 4, 5, 6, 7, 8. It's only a whole number. So it's really likely that people are going to land on the same number. Now, if you're doing how tall someone is to the centimeter or quarter centimeter, you're less likely to have people land on the same value. But if I'm doing like ages of elementary school kids, they're going to be like 6, 7, 8, 9. It's going to be very, even though the age is continuous, our scores are very discrete-ish, discretized, or only certain numbers. So the geom count can help with that. That is the whole chapter. What do you guys think about correlation? It's okay? It's okay. All right. Do we want to have a 5-minute break to stand up and shake our legs, walk around, get a drink before we start regression? Yeah, I'll pause the recording. Is there a pause? There is not a pause. Okay, we'll keep it going. I'll get our next slides up. Got some caffeine in there?
No, just water, but I need some.
Oh, some days it's a struggle.
So bad.
Yeah.
Yeah. It's not practically class time.
Oh my gosh. It's a struggle.
Do better at like 7:30 a.m.
Oh, I am not an early person. But it's the mid-afternoon lull.
Yeah.
That's why I have my huge Diet Coke. And you like the shoes? Have I worn these shoes to class before? Oh, I'm sorry. Everyone laughs when I wear them to work. They're my comfy shoes, but I have orthotics in them, and they rub on the bottom of the... I just squeak really loud. Very, distracted by it myself. Less test if it's less than 0, so negatively correlated.
I swear that's the same. Count instead of point. Maybe I should do
I don't think that matters. That shouldn't matter.
Let's see.
Sorry, I'm just getting blank screen.
Okay.
Data before? Same one, was it?
Yeah, that's always a good start. And then I would run one piece at a time. So yes, you have your data set. Ink space less than 30. Let's see how many people that would be. There, okay, we got some people. And this should draw out our grid. Yeah, ink space, inks post. There you go, it's there.
I just like
I think you had to run everything above was the thing. Yeah.
Right.
Yeah. But then he did count, so see some of his points are bigger because they've overlapped on top of each other. I like the count a lot. I always default to using the count, and if they're all the same size, then I go back to point.
I don't know this.
Okay, so here you've got the name of a data set and a pipe, and then you have the assignment after that. Okay, so here, if you were making a new variable, you have to do that within mute want to do the mean of those. So it's row means. And we usually, inside of dply or mutate, use the equal sign instead.
When we finish running these, I'll catch up.
So that's going to take your data set, and at the end, it's going to have a new variable called Angst mean. Okay. And then we want to do table.
0.3 is medium. I'm like, what?
Yeah.
So 0.5 is strong, but then it's not a 3-tiered question. Or
Yeah.
it's 4 tiers.
And then, yeah.
So it's like somewhat strong, moderately strong.
There you go. So there's your correlation matrix.
So this mean is
Okay, so the row means, yeah, because it's,
okay.
okay. Oh, yeah. Fix my spelling error. Yeah. Yeah.
I have a question on these where it's very strong and moderately strong.
Yeah.
How judgmental is this?
Yeah.
Looking at the G power thing, there's only 3 choices,
Yeah.
and like 2 of them I think are like.
Yeah. That's
medium
why.
is like, well, is that moderately strong or is that?
This is the
somewhat
book
strong?
question. The asking whether it's strong, moderately weak. That's all the book's lingo. It's not my lingo. I mean, there's just no strong cutoff. What's the correlation number? Tell me the number. That's
Yeah,
better.
well, I do that
Yeah.
later.
Oh,
So
so
I'm
so you're
like,
just
well-
eyeballing it. Yeah.
Yeah, eyeballing it, and then eyeballing
Just guess.
it, and then going back and looking at what
Yeah.
was it really? Was I right?
Yeah. Yeah.
I don't know.
That's why I'm excited to have you check your answer, because it's like, and then I changed the wording, like I gave you more options. It should be like a slider, right? And anything in this zone is like, it's not one magic number. Yeah. Okay. I think we might finish chapter 10 today and then be totally caught up. How would that be? Do you guys have questions on the homework 9 you want to talk about? Not yet? Not due till Monday, so nobody's done. The holiday weekend has snuck into the middle of the week. Okay. All right, well, then we'll cover chapter 10, and then we'll definitely get some office hours set up. Okay, so regression. The next class you're going to take, assuming you're taking them in the series like you should, is a whole class on regression. So today we're just going to touch on regression because we're doing correlation. And the whole reason we're doing correlation is to move from a 2-sample independent t-test to a paired t-test. That's the reason it's in this order for this class. Oh, I don't want to read that much text. Okay, correlation. So we just talked about correlation. Correlation tries to capture the relationship between 2 variables. We don't have an outcome. We don't have a predictor. We just have 2 variables measured on the same individual, and we want to know, do those 2 things go together or not? And so we talk about the strength and the direction in words, and then we calculate this number R and the p-value to go with it to measure how strong do 2 things go together, and is it statistically significant? So that's correlation. Regression is highly related, but in regression there is definitely one of the variables is an outcome variable, and the other variable is a predictor. So when we did correlation, order did not matter. And when we did our core.test, and both of the variables came after the tilde wave, and it did not matter which order they were in. When we do regression, order matters. We've got an outcome and a predictor, and one of them goes before the tilde and one of them goes after the tilde, and it makes a big difference if you switch them. So we are only going to do simple linear regression. That's when you have one predictor and one outcome. And we're assuming they're both continuous, normally distributed. When you take the next class, you do multiple linear regression with multiple predictors of an outcome. And you do logistic regression where the outcome could be a yes, no, or all kinds of complexities. So the basics. The y variable, we usually use the letter y to be the outcome variable, and it's also languaged as the dependent variable. All of those words, phrases, that all language is the same thing. The outcome is the dependent variable, which we use the letter y. So saying any of those things means the same thing. Mathematicians, statisticians call it an outcome more often than not. Applied statistical folks and researchers usually call it the dependent variable, but they're talking about the same thing. So that's what comes in front of the tilde wave. After the tilde wave is the x variable. The x variable is also called the predictor or the independent variable. It is also sometimes called a covariate. Usually we call it a covariate when it's not a fundamental research question, when it's more like a nuisance variable where words and phrases are all meant for the same thing. The outcome, y dependent variable, comes first. Then we have a tilde wave, followed by the predictor, the x variable, the covariate, whatever we're going to call it. Okay? Order matters big time. Now, in correlation, what were some other things that were important? Shape of the relationship. On the scatter plot, we assumed it was linear. And if we had an outlier, could throw things off a lot. Same thing applies to regression. We're assuming a line is going to fit the data, that the shape is linear, and that there are no outliers. An outlier can change R, an outlier can change regression. That's true of both of those types of analyses. Okay. So this is the way we write the equation of a line. When you had algebra, what grade did you have algebra in? 6th grade, 10th grade, 11th grade, something like that. What was the equation of a line? Y equals mx plus b. That's how we wrote the equation of a line. I taught high school algebra for several years before I got my master's degree. I taught college algebra, 1050 is what it is here, several years when I was getting my master's degree. Y equals mx plus b. In statistics, we switch the order. Y equals, oh, and we're going to call not m and x, not m and b, we're going to call m, the slope, we're going to call that b2. Because we're having fun times, right? We don't want more letters. And so the first time I learned the first statistics class I ever had was when I started my master's degree in statistics. And this threw me for a loop. I'm like, what the heck? What happened to m? M is now another b. And instead of having mx come first and plus the y-intercept be last, we're going to switch the order. And the reason, it took me a while to learn this, the reason they do this is because usually we don't just have one predictor, we have lots of predictors, but we only ever have one intercept. So that's why they put the intercept first in statistics. So the first after the equal sign is b with a little 0. That lowercase b with a 0, that's the y-intercept. That was the b in our algebra formula. The b with a little 1 here, that's the slope that we used to call m. Now, the reason we put a little 1 there is if we have another predictor, say z, that's what they do, they use another letter, we would say that its slope was little b with a 2 on it, and 3 and 4, and we can keep going on. So that's why 0, 1, 2, 3, 4. And they call all of these things betas, or parameter estimates, or slopes. Yeah, it's fun. So notice our y. What's funky about this y? Has a hat on it. Because when you estimate, you have to put a hat on it. When you estimate, you have to put a hat on it. So this says the estimated value of y is equal to the intercept plus the slope times our predictor. Because we can never say for sure what any one person is going to get, for sure. But we can estimate it, and we can have a confidence interval around it. So that's why the hat is there. So the hat is the predicted, not these observed, but the predicted value of y for any case. B with the little 0 is your y-intercept, and V1 is the slope. And sometimes they'll put the letter x or y on the B, but I don't see that very much anymore. And x is our predictor. So let's do an example. Oh, that's some more stuff. We've already talked about this. Correlation and causation, are they the same thing? Nope. Some important things. All your points, do they fall exactly on the regression line? Never, because if that happened, you wouldn't need a regression line. Does regression work equally well for every data point? No. Yeah, we need to do an example. So that's just a lot of words. Okay. Standard error of estimate. I'm going to skip that. Line of best fit. Okay. There is a data cloud, a bunch of points, and a regression line drawn through it. Are all the points on the line? No. Can you see those little lines? So some of the points are above the line, and some of the points are below the line. So I've done little lines from all the points to the regression line. So above, those are positive residuals. Residuals are how far away the points are from the line. These are negative residuals. They're below the line. Guess what happens if you add up all the residuals? 0. So if the way we can think about the regression line, the computer doesn't do this because it does a shortcut, but it's like it tries all possible lines and it finds the line that has the smallest total of residuals, but not just adding them up, because if you add them up, it gets 0. So it adds up their squared values to cancel out the positives, so the positives and negatives don't cancel each other out. It's called the minimum sum of squares. Okay, so there's a scatter plot. Can you see the points? They're kind of light. There I've drawn the regression line. Then I got some dashed lines going up and down. Those dashed lines are the averages of each of the variables. So down here I have my x variable. The average of x in my sample is 4.2. And the average value of y is 14.4, I'm guessing here. If you take the two averages and draw flat lines, this is called the point of averages. I don't know if this is in your book. Is it? It was. The point of averages. The regression line will always go through that point of averages. So if you do average on x, average of y, boom, there's one point that is always on the regression line. Now, if we think about the data cloud as just a cloud, think of the shape of the cloud. If we have a bivariate normal distribution, remember that mound that we looked at in the correlation? If you do point of averages, the points will be roughly a football shape. Okay? This point of averages always has the regression line. Now, it would make sense to me. The best line would go through the points of the football. But it doesn't. This is not the regression line. Okay, so let's see. So this is the point of averages. So when we write a point, we say it's x number and it's y number. So what's the x number for this? X bar. And if this is y, what's this y value? Y bar. So that's the point of averages. Point of averages. And the line that would go perfectly through the football is called the standard deviation line. It goes up one standard deviation and over one standard deviation. That's the slope. Now, going back to our algebra days, I have fond memory of algebra. How did we calculate m, the slope? What were you taught? Slope is rise over run. Somebody remembers. I've taught this so many times to so many hundreds of kids. M, the slope, is rise over run. Which direction do we rise in? X or Y? Y. So this is our change in Y. And we use the triangle to mean change in math and stats and chemistry. Which direction do we run in? X-axis, Y. So if this line, regression line, went through this like rise run of the standard deviations, go through perfectly through the football, this would be, let's see, how do we show the standard deviation of Y? What would I write for the standard deviation of Y shortcut? S with a little y and S with a little x. So that would be the slope if we were trying to make this line go through perfectly the points of the football. But that's not the regression line. The regression line is flatter. That would be the regression line if the correlation was perfectly 1. The weaker the relationship, the flatter that line gets. So this is the formula. If you can see those little tiny letters, this needs to be bigger on the slide. This is the formula for the slope. And for slope, we use b with a little number 1, because we're only doing one predictor in this class. So this is the formula for slope. You do standard deviation of y on the top, standard deviation of x on the bottom, but that fraction is times the number r, because that's what flattens it. Because r is a decimal number, and when you times by a decimal number, it gets smaller. So standard deviations and r. Do we know how to calculate those in the computer? Do we know how to get the letter r from a data set if we have 2 variables? Yeah? We do core.test. Can we get the standard deviations? Yeah? What's one way we can get standard deviations out of data in R computer? I've taught you like 3 or 4 ways. There's a formula.
We can use formula or we can send it as SD.
We can write SD. You can do table 1. You can do psych describe. Do you remember these things we've learned for a while? Yeah. So, but these are the kind of hand calculations you could be asked to do on homework or tests. If you had the summary information, you could plug them in and calculate the slope. Now, what do we do? Do you remember in algebra days when we were doing y equals mx plus b, and the teacher would give you like a whole sheet of these problems and be like, here's the names of 2 points, 1, 2 and 5, 37. Find the equation of the line. You remember doing that? So sometimes they'd give you 2 points, and you'd have to find the equation of the line. Sometimes they'd give you 1 point and a slope. Do you remember doing that? What do we know about the regression line? We know the slope is not quite that. We know the slope is r times that. R times standard deviation of y over standard deviation of x. That's our slope. So we have a slope for the line. We also know that the line will always go through the point of averages. So what's the equation of the line? Y hat equals b0 plus b1 x. Well, x and y, you can plug in the point of averages. And slope, you can plug in here. You'll have everything plugged in with numbers except for b0. How do we get it alone? You subtract this piece over. Look at this. Here it is written in algebra. To find the intercept, that b0, what do? You take the average of your y values and subtract slope, that we calculated right there, times the average of your x values. So these 2 formulas, slope and y-intercept, these are how you could do regression by hand. What would we need to do this? We'd need both variables, averages, both variables, standard deviation, and the correlation. We can get means and standard deviations with table 1, and we can get correlation with core.test, and so you could do this by hand. And you could make the equation of the line. You have to do that on the homework. Okay. Now, We're getting. Okay, so we talked about residuals. Now this, this is one of our last slides. We only have 5 minutes, so just hang with me 5 more minutes. Okay, so there's that red regression line. Right now I've drawn green vertical lines. That connects the points to what? To the average of y. So those are the sum of squared residuals total, how much all the y values vary around the average. We call that the sum of squared residuals. So sometimes it's SSR, sometimes it's SSE, SSR, SST, or SS total, sum of squared total residuals. Now I'm going to show you a different kind of line. Look close, it's going to change colors. What color are we going to go to now? What are those blue lines connecting? The regression line to the average, that's the sum of squared explained. That's how much of the variance is explained by the regression line. Are those two the same? Is that equation sign, is that equal? Were those green lines and these blue lines the same? No. What have I left off? Let me go back. Here's the green lines. Here's the blue lines. Oh, this is SS unexplained. So all data in our data set, are the y values all exactly the same? No, they're going to be different. People have different recalls. And we want to know, is that explained by their mood? So we take the total variance and we split it into, and variance is equivalent to sum of squared, we split it into 2 piles. The pile that's explained and the pile that's unexplained. We're going to do the same thing when we do ANOVA, which is like every day of this class after this, after the next lecture. Okay, so that's all we need to know there, is that sum of squared total gets split into the sum of the squared that's explained and the sum of the squared that's unexplained. Explained is the regression line and residual error. Okay, so sometimes when we do regression, we talk about the R squared. Have we done R squared today? No. What have we talked about R, the first half of today? We talked about R as in the correlation coefficient, just plain R. This R is squared. Huh? It's not point biserial correlation. That's if you have a continuous variable with a dichotomous variable. Binary variable. This is R with a 2 up here floating, the squared. Numerically, if you know what R is, if R is 0.7, how do you get R squared? 0.7 times 0.7 times itself. So number-wise, that's what you do it. But that is called, when you square R, the correlation, that is called the coefficient of determination. Sounds important, doesn't it? Yeah. It is the fraction of variance that is explained. It tells us the percent, if you times it by 100, the percent of variance that's explained by the model. So it helps us tell, is mood, correlation tells us, is mood related to recall? Coefficient of determination tells us what percent of the variation in recall is explained by mood. Okay, I'm going to skip the standardization. We'll do that next time. We got 1.5 minutes left. Okay, R, just so that if you want to start the homework you can. Let's see this crazy code. What do we start with? Name of the data set piped in. Okay, are we seeing a pattern? This command is really short. LM. It's part of base R. This stands for linear model. It's doing linear regression. They could have said LR. LM. Remember when we had our scatter plot, how did we put the straight line on? We said geom smooth method equals LM. It matches. It's doing the linear regression. LM. Now, what do you notice about this formula? We have 2 variables, but one's coming before the tilde wave, one's coming after. The one that comes before is our outcome dependent variable. The one that comes after is our independent variable or predictor. Lots of times we have lots of things over here. That's multiple linear regression. That's 7610. But we're only going to have one thing here. Data equals dot. Now, it will give you only the tiniest bit of output then. If you want more output, which you need, you have to then pipe on the word summary to give you more output. Okay? So this is what you're going to do several times on the homework. So there's the output. What in the heck does that mean? There's a lot of stuff there. Let me point out some things. Right down here, it says multiple R squared, because usually we're doing multiple regression. But just ignore the word multiple, because we only have one predictor here. This is the R squared. It says R squared, isn't that nice? It says a capital R, but it means little r. It's inconsistent. But what is that number? It's about 0.5. This is the coefficient of determination for this model. So this tells us that the x variable explains about half of the variation in the y variable. That's a pretty good chunk. And that's an important thing to report when you're reporting a regression model, is this coefficient determination or this R squared value. Again, the multiple just is because usually we have multiple predictors. It's rare that we only have one. There is an adjusted R squared. That's adjusting for model complexity, which we don't have, so we're going to ignore that. So that's important. Okay, this middle chunk here is the last thing. I'm just going to point this out as we are going over time. The intercept, it says intercept. See, it says the word intercept right there. And then it says estimate. So this number right here, this negative 0.017, this is the estimated intercept. What symbol do we use over there for the intercept? B sub 0, B naught. So this is your B naught, your y-intercept. And if you look all the way at the end, that's its p-value. Then here it says x, which is our predictor. Here's its slope, 0.95. And it has a p-value. Okay. We'll leave it there, and we'll pick up finishing regression on Monday, and we'll do the paired t-test. Good? Okay.